This is video number 18 in a series about complex arithmetic, methods and geometric interpretations. Actually, in this video, we're not going to focus so much on the complex numbers as just checking what we did in the previous video, checking how we applied an exponential representation of the cosine function involving the imaginary unit to the evaluation of a real integral. Down here is the problem that we did. We looked at trying to evaluate the integral of cosine cubed. And the trick we use this exponential representation of the cosine function in terms of the imaginary unit I. We replace the cosine function with it. We cube that by taking the 1/2 and cubing it to become a 1/8 that we bring out here. And then using the binomial theorem to expand this expression, e to the I theta plus e to the negative I theta to the third power, using the binomial theorem to expand it like this. Then in our minds we thought about this. You certainly could write it out using Euler's formula, but by thinking about it, we realized that we could simplify this pretty quickly using Euler's formula in our heads by realizing that because of the form of this, the fact that we have these two terms matching up and these two terms matching up with positive and negative signs, that the sine functions would cancel out, the imaginary parts would cancel out, you'd only get cosine terms. And this is what you would get when you expand it out. And if you didn't see that in the last video, or if this is new to you, you should make sure you use Euler's formula to check this. That's a pretty easy integral to do, and here was the answer that we got. And then we looked at the graph of both the original integrand and the proposed antiderivative. We did the integrand in red and the proposed antiderivative in blue, and we looked to check the reasonableness of our answer. So again, to check that, it should be the case that the derivative of the blue is the red, so the slopes of the blue are given by the values of the red. Positive slope over here, negative slope in here, etc. And it looked reasonable. In this video, the main point I'm trying to make is that we can check this in another way and be more sure in our checking. And this other way is going to involve evaluating this integral, first of all, in a way you might have learned in calculus. First of all, write the cosine cubed theta as cos squared theta times cosine theta. And by the way, if it was not clear before, when you see something like cos squared theta, it means take the cosine of theta first and then square it. Hopefully you remember that. Then by the fundamental Pythagorean identity that cos squared theta plus sine squared theta equals 1, you can replace the cos squared theta with 1 minus sine squared theta. And then, once you've done that, this is set up very nicely to do a substitution. You would let u equal sine theta, and then du would equal cos theta d theta, and you'd get a 1 minus u squared here, and a du here. So you'd ultimately be integrating. You might want to pause the video and write that down, but I'm going to delete this now. You end up getting the integral again of 1 minus u squared, which would be u minus u cubed over 3, which after replacement back with u equals sine theta, you would get sine theta minus 1/3 sine theta cubed plus c. So evidently this is equal to the integral as well, but it certainly doesn't look the same as this. So how are we going to match them up? Are they really the same function? It turns out they actually are. Trigonometric identities are all over the place, and because of it, it makes checking trigonometric integrals oftentimes difficult. If you do it different ways, the answers look different. However, these are the same. I mean, theoretically it's possible that it could be different up to a constant, but they are going to be the same function up to a constant at least. And to check it, what I can do is I can use the exponential representation of the sine function and do that replacement here, cube out the sine function, and we would see if we simplify it that we'll get this, and that's what we're about to do. So let's do that. And to save some time here, I'm trying to make this video a little shorter. I'm going to use Mathematica to actually do the calculation for me using Euler's formula. First of all, if I use complex expand, I'm going to be thinking about sine of theta cubed, so I'm going to take this thing and cube it right there. So I think I'll type it in like this. Capital E is the number E. I can use capital I for I, or again the escape, I escape. I'll use capital I to save a little time. So this is the sine function. Right there, and I'm cubing it. Looks like my parentheses are matching up. Pause the video and think about that again. I'm using this formula right up here. Cubing it, because I want to get sine cubed theta. This does confirm it's sine cubed theta. To get it to look more like I want, in other words, for example, to get a sine wave with a period of 2 pi over 3 in it, I can now do trig, not expand, but trig reduce will get me what I want here. There it is. So this is showing that sine cubed theta, which again means sine of theta quantity cubed, can be written as 3/4 sine theta minus 1/4 sine 3 theta. And now that means that this function here, I don't know if this is going to end up being red or not. Oh, there we go, not red. Can be written as sine theta minus 1/3 times, in parentheses here, I'll go ahead and copy and paste this whole thing, that distributing the 1/3 through, 1/3 times 3/4 is going to be 1/4, and I've got a minus sign, so I've got a minus 1/4 sine theta, and then a plus sign from negative 1/3 times negative 1/4 plus 1/12. This is looking good. Plus 1/12 sine 3 theta. Simplify a little bit more, and you do indeed get this thing here. So they are actually the same with the same constant. This function and this function, ignoring the constant, are the same function. And so we have checked more rigorously that the integral that we got using this exponential representation of the cosine function is correct. In the next video, we're going to get into powers of complex numbers, and probably in the video after that, we'll get into roots of complex numbers, getting to section 1.5 of the Saff and Snyder book.